Welcome to another video of OptaTube. Today, we're diving into something really cool, a digital twin of the entire power grid. We're going to explore what it actually takes to keep the lights on in our super complex modern world. So let me just start by asking you a question. What if you were the one in the control room? What if you got to pull the levers, set all the parameters, and basically manage the flow of electricity for an entire region for one whole day?
Well, today, that's pretty much what we're going to do. Now, obviously, we're not going to mess with the real grid. That would be bad. But we are going to play around with a really powerful simulation, a virtual copy that acts just like the real thing. Okay, let's jump in.
So the main idea we're talking about here is called a digital twin. Honestly, the best way to think about it is like the ultimate video game, or maybe a super detailed interactive sandbox, but for the power grid. It's a full-on virtual model of the electricity market that lets us run experiments, test out different scenarios, and see what happens, all without any risk to the real world. Now, just like in any good game, our simulation has its main players, and each one has a totally different role, different strengths, and, different things that motivate them. If you can understand them, you can understand the grid itself. First up, you've got your thermal generators. So think coal, gas, nuclear plants. These guys are the steady, reliable workhorses of the whole system. They provide that foundational power that we can count on, day or night, rain or shine. Next in line, we have renewables, so wind and solar. And when the sun's out and the wind is blowing, oh man, they are incredibly powerful and of course clean, but here's the catch, they're variable. Their output completely depends on the weather, and that throws a big dose of unpredictability into the mix that somebody has to manage. And that is exactly where our third player comes in, battery storage. What's so cool about this player is its role, it's like a savvy opportunist. It plays the market, it soaks up all that cheap excess energy like on a super sunny afternoon, and then it turns around and sells that power back to the grid later when demand is high and prices are way up. It's the ultimate balancing act. And finally, we've got the rule setters, the TSO and DSO. That's the transmission and distribution system operators. Now, they're not making any power themselves, but they are managing the highways and the local roads of the grid. They're the ones preventing traffic jams, what we call congestion, and making sure power gets where it actually needs to go. All right, so we met the players. Now it's your turn. It's time to take a seat in the control room, because for this simulation, you're the one in charge. You get to set the starting conditions for our 24-hour scenario using these control sliders. Let's take a look at our control panel here. We can set the base demand for the day. We can decide the renewable share, how much of our power is coming from wind and solar. We also control the storage capacity, basically how big our battery is. And this is where it gets really fun. We can simulate grid stress with sliders for TSO congestion and DSO load management, which lets us create bottlenecks just to see what happens. Okay, the parameters are locked in. The players are on the board. Let's hit run and watch how this day plays out on our digital grid. And we're off! Right away, as the simulation starts, we see the classic morning ramp up. People are waking up, businesses are opening their doors, and electricity demand starts to climb. And to meet that rise, our reliable thermal generators just scale up their output, keeping everything nice and stable. Then, boom, we hit midday. The sun is at its highest point, and all of a sudden, our renewable generation just surges, flooding the market with tons of clean, cheap electricity. A lot of the time, this is way more power than the grid actually needs in that moment. So, the big question is, what do you do with all that extra energy? And right on cue, our opportunist player makes its move. The battery storage system just springs into action and starts charging up, soaking all that cheap, abundant solar power right off the grid. This stops that energy from going to waste and saves it for, well, not a rainy day, but, for when the sun goes down.
But then, a problem. A challenge pops up in the simulation. The main transmission lines are getting congested. It's basically a grid traffic jam. The TSO has to step in and tell some of those reliable thermal plants to power down to keep the system from overloading. This creates a kind of artificial scarcity, and you can see the market prices start to spike because of it.
And just like that, our 24-hour run is done. We've navigated the morning rush, we've managed a huge surge of renewables, and we dealt with a grid traffic jam. That was a full day in the life of the power grid, all simulated in just a few minutes. So, what was the point? What did we actually learn from being in the control room? Let's get to the debrief and see how this all adds up, and why running a simulation like this is so important in the real world. The first big number that jumps out at us is the average market price for the day.
In our simulation, it was just under 50 euros per megawatt hour. You can think of this as the final score for the day. It reflects the total cost of balancing supply and demand through everything we just watched.
But if we dig a little deeper, we get the whole story. We can see the total demand and exactly how it was met by that mix of renewables and thermal generation. We can see how much our battery had to jump in, and check this out, the frequency fluctuation. That's a super critical measure of grid stability that operators have to manage literally second by second.
So what are the big takeaways from all this? Well, first, we saw with our own eyes that traffic jams on the grid can cause prices to spike, even when there's plenty of power available. We also learned that how local networks are managed has a direct impact on whether batteries make financial sense. And finally, we saw how a bigger share of renewables, while amazing for the planet, also adds a ton of volatility that makes balancing the grid a constant, high-stakes game.
You know, this kind of modeling is absolutely critical for designing the grid of the future. It lets us test everything out and perfect the systems we're going to be relying on for decades. And hey, if you find this stuff interesting, energy markets, power system modeling, or just want updates and insights on the global energy market, you should definitely follow the OptaTube YouTube channel.
And all of this leaves us with one final, pretty big question to think about. We've seen just how powerful these digital twins can be. So as our energy systems get more and more complex, who should get to control the simulations that are going to shape our energy future? It's definitely something to think about. Thanks for watching.